Welcome back, and today we are going to start talking about a special two types of solutions, acids and bases. We've talked about solutions and concentration in the previous few videos. Now we're going to take that information to talk about a specific kind of solutions that we deal with a lot in chemistry, acids and bases. So there are two main models or definitions of acids and bases. We have what's called the Irenaeus model and the Bronsted-Lowry model. So these two different kinds of ways are two different ways of looking at what is an acid, what is a base, based off their definitions of how they define these two different types of solutions. Pretty much all acids and bases are going to fit both of these definitions. It's just a different way of looking at the solutions themselves. So let's look at the Irenaeus model first. It was developed by a Swedish chemist named Svante Irenaeus back in the 1880s. And what Irenaeus did was he created his model where he said an acid is defined as a substance that contains hydrogen in its chemical formula and ionizes in aqueous solution to produce hydrogen ions. So when you put it in water, it's going to break apart into a hydrogen ion and its anion. So you're going to have hydrogen ions floating around in your solution. That is what was defined as an acid. So this example, we have hydrochloric acid, HCl, or hydrogen chloride, will break apart into H plus ions and Cl minus ions when in aqueous solution. It's going to ionize, producing H plus ions. That's what makes it an acid according to the Irenaeus model. The Irenaeus base is defined as a substance that contains hydroxide in its chemical formula, and therefore it will dissociate or ionize in aqueous solution to produce hydroxide ions. So same thing that hydrogen ions do, it's going to, though, break apart and form hydroxide ions. So you've got sodium hydroxide here is going to break apart and give you sodium ions and hydroxide ions in aqueous solution. That's what defines it as a base in the Irenaeus model. So your Irenaeus model is based off of the ionization and whether it produces hydrogen ions or hydroxide ions. Hydrogen ions will be an acid and hydroxide ions are going to be a base. The Bronsted-Lowry model looks at things a little bit differently. Same basic idea, but it just looks at it from a different perspective. So it was created independently by both Danish chemist Johannes Bronsted and an English chemist named Thomas Lowry in 1923. Now they did this independently, so they didn't really work together. They both published their papers, and so we named it together. All right, their model focuses not on the ionization of the formulas, but on hydrogen ions specifically, which are basically just protons. So if you remember, a hydrogen is one proton with one electron circling around it. Well, if you take that electron away, you have a hydrogen ion. So a hydrogen ion is just a proton floating around. So when we're talking about hydrogen ions in the Bronsted-Lowry model, oftentimes they just refer to them as protons because that's what a hydrogen ion actually is. So in the Bronsted-Lowry model, an acid is defined as a substance that acts as a proton or a hydrogen ion donor in aqueous solution. So it's something that will produce or donate hydrogen ions or produce or donate protons. It's a proton donor in solution. So the Irenaeus model also still kind of fits that because when I put something in water and it ionizes, it's producing hydrogen ions. So the Bronsted-Lowry model looks at it slightly different, not just that it produces the hydrogen ions, but it donates those hydrogen ions to something else. And that's what makes it a proton donor, is an acid in the Bronsted-Lowry model. Now, a Bronsted-Lowry base is the exact opposite. Instead of being a proton donor, it's a proton acceptor. So it acts as something that will take those hydrogen ions from other things. Now, if you think about the Irenaeus model and how that fits, something that produces hydroxide, well, an OH minus ion is going to accept a proton from another thing to produce water. We'll talk about that more a little bit later. But a hydroxide ion will accept a proton, accept a hydrogen ion, and so therefore a hydroxide ion is a proton acceptor and therefore a base. So if they basically say the same thing, why do we even need the Bronsted-Lowry model? Why was it necessary for them to come up with a different way of defining acids and bases from the Irenaeus model? Well, Irenaeus model says that a hydrogen ion or a hydroxide ion is produced, meaning a compound will contain hydroxide. Well, what about something like ammonia? Ammonia is NH3. Ammonia is very much a base. It behaves just like a base, has all the properties of bases, it treats things like a base, but it doesn't have a hydroxide group. So how does that fit the definition of a base? It doesn't really fit the Irenaeus definition because it does not contain hydroxide. However, whenever ammonia is dissolved in water, it's going to take that an extra hydrogen from the water and become NH4 plus, ammonium. And that will then become a proton acceptor. Now, the end result is that it also, since it steals a hydrogen from water, it actually makes hydroxide in solution. So it kind of still fits the Irenaeus definition in that it still makes hydroxide ions, but it's not part, the hydroxide ion is not part of the ammonia molecule, and therefore it doesn't really fit the Irenaeus definition, but it does fit the Bronsted-Lowry definition of being a proton acceptor. So let's talk about some characteristics of acids and bases. How do we define something as an acid base, or how can we identify it as an acid and base based off some different properties? So first off, taste. Now in an actual chemistry lab, you should never, ever, ever taste any of the chemicals. But if you're at home and you want to know whether or not the stuff you're eating or drinking is an acid or a base, you can tell based off the taste. Acids are going to taste sour, like lemons and limes and grapefruit. They have acid in them. In fact, it's citric acid. That's why they're called citrus fruits, because they contain citric acid. And that acid is what gives them their sour flavor. Bases, on the other hand, are things like soap or baking soda. If you were to ever taste that, they taste bitter. So bitter tastes kind of like soap. If you've ever gotten soap in your mouth and tastes bitter. Soap is a base. A lot of cleaning products are bases. The chemical formula can also help you know whether or not it's an acid or base. Acids are pretty much always going to start with an H+, because they, in both the Bronsted-Lowry and the Irenaeus definition, in order to be an acid, they have to be able to donate a proton. So they have to have that proton to donate it. And that proton is a hydrogen ion. So hydrogen ions, if you remember way back when we talked about nomenclature, acids were anything that had hydrogen as a cation. And so that's still the way you look at it. A chemical formula, if hydrogen is the cation, then it is pretty much an acid. It's going to be able to ionize into hydrogen ions and something else and be a hydrogen ion donor. Bases are nearly always going to contain hydroxide. Not every single time, but most of the time. And if something contains hydroxide, it's a pretty good indicator that it's probably a base. Now, bases not quite as 100% as with acids in the formula, because acids, if they have hydrogen as the cation, it's pretty much an acid, but bases not so much. And like we just said with the ammonia, not all bases have hydroxide. So it's not as clear of an indicator, but it's a good way to help identify something. If you see lithium hydroxide or potassium hydroxide or iron hydroxide, something with hydroxide in the name is probably a base. Litmus paper is a way that we can tell whether or not something is an acid or a base. So what is litmus paper? It's an example of what's called an acid-base indicator. So litmus paper comes in two varieties, either red or blue. And I know you probably can't tell that much on the screen. They're not really red and not really blue. It's kind of more pink and purplish, but we call them red and blue. It comes in these two varieties. And an indicator is a substance, we're going to talk about indicators more in a later video, but an indicator is a substance that will change color based off the presence of being in an acid or a base. So acids will turn blue litmus paper to red. So I'm going to give you an example. I have some acid here, and I'm going to use a red litmus paper, and I'm going to put it in there. And you'll notice that when I do that, it doesn't really change color. It looks a little bit different, but that's mainly just because it's wet. But if I take some blue litmus paper and I put it in the acid, that blue litmus paper is going to turn a completely different color. It's going to turn red. So the blue turned to red. So a acid will turn a blue litmus paper red, whereas a base is going to do the exact opposite. A base is going to turn red litmus paper to blue. So if I have a base, and I'm going to show you what it looks like with blue, if I put blue litmus paper in the base, it's still blue. It's just wet. It doesn't really change its color. But if I put the red litmus paper in the base, then it will turn blue. So an acid will turn blue litmus paper will turn red, and in a base, red litmus paper will turn blue. So you kind of have to test both of them, red and blue, to know if it's an acid or base. You put the red in there, see if it changes color. If it does, red turns to blue, it's a base, and if your blue turns to red, then it is an acid. Now, pH is another way that we can tell if something is an acid or base. And again, we'll talk about pH more in a later video and talk about how to calculate it and all of that. pH basically just stands for potential of hydrogen, and so it has to do with how much hydrogen ions there are. So a pH less than 7 is acidic. A pH greater than 7 is basic. A pH equal to 7 is neutral, meaning it's not either an acid nor a base. And there are a lot of things that are neither acid nor base. So just because if we're testing the pH, if it comes out neutral, that doesn't necessarily mean it's water. Water is neutral, but water is not the only neutral substance. There are a lot of neutral substances when it comes to acidity. So less than 7 is acidic, greater than 7 is basic. Corrosiveness is another thing that we often associate with acids. Corrosive substance is one that will damage or destroy other substances with which it comes into contact by means of a chemical reaction. So if I put something in the acid is going to eat it away. But the thing is that acids and bases are both corrosive. So it's not a defining characteristic of either. Unfortunately, a lot of people think of acids as corrosive and bases are not, but that's not actually true. If you have a concentrated base, it can be just as corrosive as a concentrated acid. In fact, Drano, drain cleaner that you put down your sink to dissolve and corrode away a clog in your drain, those are usually always bases. They're highly concentrated bases that will corrode away. And the issue is they don't react very well with the metals in the pipes, and so therefore you don't have to worry about them necessarily destroying your pipes. No, they can over time and with a lot of them because they are still corrosive. Again, acids and bases are both corrosive when they are concentrated, so you can't use being a corrosiveness as an indicator of whether something is an acid or base. When it comes down to acids and bases are about hydrogen ions and hydroxide ions. Neutral solution, the pH of 7, means the number of hydrogen ions is equal to the number of hydroxide ions. In an acidic solution, a pH less than 7, your number of hydrogen ions is greater than the number of hydroxide ions. So acids have more H plus in them. Again, the Bronsted-Lowry model says an acid is a proton donor. The Irenaeus model says acids produce hydrogen ions. So they're going to have more hydrogen ions than hydroxide ions. So a basic solution is going to have less hydrogen ions than hydroxide ions. So if a base is a proton acceptor, it's going to take those hydrogen ions out of solution, and hydroxide, if it's there, is going to take those. And so you're going to have more hydroxide ions than hydrogen ions, and so you have a base. So this is how we look at whether something is an acid or base based off the hydrogen and the hydroxide, the relative concentrations. The relative amounts of hydrogen and hydroxide are going to make a difference as to whether it is an acid or base. So how does water fit in? Water, as we talked about previously, is amphoteric. That's a fun little word to say, but amphoteric. So remember what we said back when we talked about water being amphoteric. It means that water can be thought of as either an acid or a base. It can be both, all right? So let's look at it in terms of the Irenaeus model. In the Irenaeus model, we have hydrogen ions being produced or hydroxide ions being produced, and they both have to be part of the formula. Well, if you write the formula of water as HOH instead of H2O, then water contains a hydrogen and a hydroxide. It therefore fits the definition of the Irenaeus acid and the Irenaeus base. It fits both definitions. So let's look at it in terms of the Bronsted-Lowry definition. Bronsted-Lowry model, it donates a proton or accepts a proton. So how does that work? Something called self-ionization that water does. That allows water to be both a hydrogen ion donor and a hydrogen ion acceptor, and therefore it fits the Bronsted definition of both acid and base. It's all because of the self-ionization. So what do we mean by self-ionization? Self-ionization means that two water molecules are going to react. They're not actually reacting, but we're going to say react to form a hydroxide ion and what is known as hydronium ion, H3O+. So what does that mean? It means we're going to have two water molecules, H2O plus H2O, and they're going to react together, and one of those hydrogens is going to give up, one of those water molecules is going to give up a hydrogen to the other one, creating that hydronium ion, H3O+, and a hydroxide ion. So one of the water molecules is a proton donor, an acid, and one of the water molecules is a proton acceptor, a base, and therefore it can act as both a acid and a base as Bronsted-Lowry definition defines it. And so it is amphoteric. Now when we're talking about acids, hydronium ion is conceptually equivalent to a hydrogen ion because these hydrogen ions are not really going to be bouncing around, floating around all by themselves. They're highly reactive. So they're actually going to either join with something else in the solution and something else is going to accept it like a hydroxide, or they're going to join with a water molecule and form hydronium. So when we're talking about a solution and we're talking about the hydrogen concentration, the hydrogen ion concentration or the amount of hydrogen ions and the hydronium ion concentration, the amount of hydronium ions, are conceptually equal concepts. They're basically the same thing. We can treat things as hydronium or hydrogen ions, either one. So that's important that you know that. So this is just a brief overview of acids and bases and the characteristics of acids and bases and what makes something an acid or base in the two definitions. So make sure you remember those two different definitions, the Irenaeus acids and bases and Bronsted-Lowry acids and bases. It's very important that you understand both of them, how they are different, and how something can be identified as one and not the other, or either way. So thanks for watching and have a day.